Today we have a very interesting video. I'm going to be talking about the Taylor series, and we're going to derive the Taylor series for a function through error minimization, which is going to be, I think it's a more like intuitive approach, is going to really show you what the Taylor series is, and it's going to also show you why, these polynomial estimations of a function, why as you sum them from 0 to infinity, why they have to equal exactly our function if our function is infinitely differentiable. Because we're gonna take a method such that we're gonna first we're gonna take a polynomial of degree 1, and we're gonna find the polynomial of degree 1, which is the best possible approximation of our function f at the point A, and then we're gonna extend it to a polynomial of degree 2, and we're gonna find the polynomial of degree 2, which is the best possible estimation of our function f of x. And we're gonna keep on repeating this process. So eventually, as we get to the power of infinity, we're going to see that this polynomial approximation has to equal exactly our function f of x, because at each one we found the best possible approximation, and we're going to see that why this can't have any other shape, why this is the only shape such that it is the best possible approximation, and which is the exact function as we sum to infinity. So first of all, I mean, it's kind of confusing at first, but first just get some intuition. Here we have our function e to the x, and we're going to be approximating the function e to the x at the point a equals 0. So at the point here, x equals 0. And the first polynomial assumption, or the first estimation function, will just be a polynomial of degree 1, and that's just, as we all know, a straight line. So at the point 0, of course it equals our function, but everywhere else it's a pretty bad approximation. And then we're gonna extend this polynomial of degree 1 to a polynomial of degree 2, and we're gonna see that, oh, it's already a slightly better approximation. We can see that at the point 0 it kind of equals our function pretty well. And then we're gonna extend it to a polynomial of degree 3 and 4 and 5, and we're going to see that slowly these are better and better approximations of our function, for in this case e to the x. And we can see we can expand this at any point, not just a equals 0. We can try to estimate this function at any point we want. I'm just choosing the point a equals 0, but you can do it wherever. And if you're wondering how I found these coefficients, how I found these coefficients like e to the a over 2, and then I added e to the a over 6, like we're gonna see that through error minimization. So what do I actually mean by that? Well, let me just delete this for now. How do we actually find these best polynomial like approximations of a function? Well, let's just start with any function. As always, let's start with a classic function f of x, and I can just plot the function f of x, and it can be whatever. I'm just plotting it over here. This will be f of x, and then our first assumption, like our first kind of first approximation, which I'm going to call lm of x, or we can just have it be equal to f of a. Well, what is f of a? F of a is literally just a straight line. So again, if we choose a point over here, this is our point A, which we're going to be approximating. Well, f of a will just be a straight line, which is going to equal exactly, f of x at the point A. And obviously, these two functions, f of a equals lm of a, but only at the point A, and then everywhere else we have an error. And how do we kind of calculate this error? Well, we can take our remainder function Rm of x, and that would just equal to f of x minus our approximation Lm of x. And we're going to see that, for example, when x is over here, our error function will be this over here. F of x equals this. Lm of x, for example, equals this over here, because it's just a constant line. So our error will be this line over here. And then as x gets closer and closer to a, our error gets smaller and smaller and smaller. Our error decreases, and eventually our error function will go to 0. So at the point x equals a, this error function will equal to 0. But we want, this is the worst possible approximation we can have. We want better and better and better approximations. And we're going to see that there's actually a way to kind of see how good these approximations are, and we're going to see how to make them the best possible through limits, through the normalized error. So I'm not going to do any examples for this over here, because this is just the classic straight line. We're going to go straight into adding a second term approximation, and then we're going to see how we can make the best possible second term the best possible linear approximation, because here we know the best possible approximation is just f of a. So we want to add a second term to our function lm of x. And what will the second term be? Well, we're going to keep the first term. We're going to see we always keep the first term, and we're going to see why we actually can do that and why we have to do that. And then we're going to add a second term, mx minus a. And why do we add this term exactly? Well, for starters, if we check out lm of a, we're going to see that still equals f of a, because if we plug in a for x, we're going to see that this just goes to 0. So lm of a still equals f of a. So this kind of doesn't hurt our initial approximation. At the point a this will still be the same as our previous approximation. But what this m does is it allows us to rotate our line. Our line approximation, which I wrote in gray before, it was something like this, but now if we change m, we can make our line rotate, because this is just the slope. Again, if I this over here is just the equation y equals mx plus b, where b is the y-intercept and m is the slope. You can do this at home, but you can see it's just the same. It's a straight line equation written in a slightly different form. So m is basically the slope, and it controls how tilted the line is. So we can see that if we choose a specific m, for example, if we choose an m such that our slope function will be tilted like this, then we can see it approximates our function way better at the point A. So we want to find the best possible tilt of this line to approximate our function f of x. And how do we do that? How do we find the one that minimizes this green error the fastest? Well, we got to introduce something called the normalized error. So we're going to take the limit as x goes to a of our remainder function rm of x over x minus a, and x minus a is the normalized error. What is x minus a? Well, we know that x approaches a in a linear fashion, so x basically approaches a the slowest way possible. We have x over here, and this variable x will be approaching a. So first of all, it will be this far away from a. Then when it's going to be here, it's going to get closer. It's going to get closer and closer and closer to a. So if we actually plot x minus a, it will be this straight line over here. It's going to approach a. For example, here a is 0, but we can have a to be whatever. We're just going to be doing it at 0 now. But we want our approximation function, well, as x approaches a, we want our approximation function to approach f of a faster than x approaches a, because that's the whole point of the approximation. We don't want it to approximate in a linear fashion. We want it to, as x goes here, we want this error to go to 0 faster than this error over here. So we take this quotient, which is going to be the limit as x goes to a of our function f of x, and then minus our as I said over here, minus our approximation. So minus f of a minus mx minus a, because again, this is our first order approximation, over x minus a. And we want this to go to 0, because if this goes to 0, that means that both of these are going to 0. But if this quotient goes to 0, that means that our approximation over here goes to 0 infinitely faster compared to this normal, the slowest possible way to go to 0, which is the linear way, x minus a. So we want this quotient to go to 0, and there's only one such m that we can find such that this goes to 0. And how do we find this? Well, again, if we just take the limit, if we split this into two fractions, well, this over here, the limit as x goes to a, that's literally just the definition of the derivative of f at the point a. And then, when I divide this by this just cancels out. The limit doesn't apply to n because it's a constant, so we just get minus m. So this equals this, and this will equal to 0 only if m equals the first derivative of f at the point a. So we see that our approximation function lm of x, our first order approximation, our linear approximation, lm of x will be the best possible approximation if m equals the derivative of f at a, x minus a. So this is the best possible linear approximation. And again, we can see, that is exactly this straight line over here. It's a tangent to our function, and that obviously makes sense. And again, if I actually plot our error function, which is f of x minus our approximation over here, if I plot this error function, we can see that it goes to 0 way faster than our function x minus a goes to 0. We can see it goes to 0 way faster. So this close to x equals a, it will be negligible compared to this. So it's going to be small O of this, which means it's basically it's the only such function that this limit will go to 0. If m was anything else, for example, f of a plus 2, well, then this over here wouldn't be 0 anymore. This limit would equal a constant, for example, like 5 or 6 or 7. And if that is the case, if it equals a constant, then we can say that this function is big of this function, which means all we can say is that this function will be bounded by this function times a constant, but it won't be infinitely smaller. It won't be negligible compared to this function. So what can we do now? Well, now we can say that we want to make our approximation even better. So we want the limit as x goes to a of our function f of x, minus our approximation minus lm of x over x minus a squared. Now we want that to go to 0. And we can see that x minus a squared goes to 0 way faster than x minus a. Again, if I plot x minus a squared, we can see that this goes to 0 way faster than our original function x minus a. And now all of a sudden, we can see that our linear approximation isn't so much better. They're basically the same. If we scroll in, they're basically the exact same approximation. They're big O. And again, if we take their quotient, we're going to get 0.5, which just means that if we take this quotient, if we're trying to approximate our function, a function, let's say x squared at a point x equals 2, and we take this quotient, we're going to see that this function is 0.5 of this function, which means that it is about, half as good, but it won't be infinitely as good. So we can see that we need a better approximation than our linear term. So basically, again, and you can do this example. You can do the example of if your function is f of x equals x squared, and then you have your classic approximation, which with the initial linear approximation that we defined. If we want to do it for x squared, we're gonna get that lm of x equals of x equals, well, just 4, which is just f of 2, and then plus the derivative of f at 2, and that's obviously also just going to be equal to 2x, so it's going to be 4x minus a. This will be approximation function. If we want this over, so then if we want f of x, which is going to be x squared minus lm of x over x minus a squared, if we want this to go to 0, we're going to see it doesn't go to 0. It actually goes to, if we take the limit as x goes to 2, we're going to see that this quotient goes to 1. So it doesn't go to 0, which means our linear approximation isn't good enough anymore. And we can obviously also see this here for the case of e to the x. This approximation is not so much better than x minus a. They're basically the same thing. So how do we make it, again, infinitely better? Well, we add a second quadratic term to our function lm of x. So we're going to have lm of x will now equal to f of a plus, our initial approximation, and we keep the initial linear approximation, and then we add a term mx minus a squared. Now we add a second term, and again, why am I adding x minus a squared? Like, why am I adding this specific thing? Well, just to see if we check lm of a, this will still equal to f of a, because when x equals a, this and this both goes to 0, and if I take the first derivative of lm at the point a, well, that's just going to equal to, again, if I take the if I derive this goes to 0. Again, the derivative, of x times the constant is just the constant. And again, this, if I take the derivative, it's going to be 2mx minus a. And at the point a, this will again go to 0. So the derivative of ln at a will again just be equal to the derivative of our function at the point a. So again, this is the whole point of the Taylor series. It equals the first derivative of the function equals the second derivative of the function. And again, we can see that, we are, by adding these terms, we are exactly satisfying this criterion. So the intuition behind this is basically that, higher order terms, when x is close to a, when this is a very small number, but if it's like 0.1, for higher order terms, this will be 0.1 squared, which is 0.01. So higher order terms are negligible. So we can keep on adding higher order terms, and they won't mess up our initial, linear approximations. So basically, you already know how this game works. We take the limit as x goes to a of f of x minus all of this, so minus f of a minus f of a x minus a minus mx minus a squared, and then we want this over x minus a squared. We want this to go to 0. So now, just as we found m has to equal this for the linear term to go to 0, now we want to find an m such that this goes to 0. And how do we do this? So again, we can just use some simple limits. We can do exactly what we did before, but we're going to see that if we plug in f of a, we're gonna get f of a minus f of a, and this will be 0, this will be 0, so this will be 0, this will be 0. So we're just gonna get an indeterminate form 0 over 0, which means we can use the L'Hopital's rule, because this is an indeterminate form 0 over 0. So if this limit exists, then it will be the same as the derivative of the initial, of the numerator over the denominator. These are the same limits. So this will all of a sudden become the limit of f of x, the derivative of f of x, this just goes to 0. This just stays as f of a, because the derivative of x times the constant is just the constant. This will again go to 0, because this will be 2mx minus a, and the point a, this will just be, the derivative of this will just be minus 2mx minus a, so the 2 just drops, and then times x, which is this 1, and the derivative of the bottom thing again will just be 2x minus a. So now we get this over here, and again, if we plugged in x equals a, we get 0 over 0 again, but we can also just see that we can take this 2 out. We can split this into this fraction, and then for this, we can take the 2 out, and this, f prime of x minus f prime of a over x minus a, the limit as x goes to a, that's just the definition of the second derivative of a function. So just f double prime of a, and this over here, 2x minus a, this just cancels, so all we're left with is m, and the limit doesn't affect m. So if this equals 0, this will equals 0. This just simplifies to this when we evaluate the limit. So this will be 0 if m equals 1/2 times the second derivative of f at the point A. And we found the only m such that this normalized error will go to 0, and is this m over here. And again, if we plot this over here, if we actually plot this, which is our function f of x, minus our approximation, this is for the example of e to the x, the first term, the second term. If we plot this, we can see that this goes to 0 way faster than x minus a squared. Again, this was x minus a squared, this green line over here. I'm going to delete our first approximation. See, our linear approximation wasn't that much better, but this approximation over here we can see is way better. It goes to 0 way faster. And again, it is the only approximation that is small o of this function, that the small o of x minus a squared. So m for our second order approximation, the best possible one, we just showed why it's the best possible one. It's the only one that makes this this quotient go to 0 as x goes to a, would just be f of a plus f prime of a x minus a plus 1/2 times f double prime of a x minus a squared. And now we can continue playing this game. Now let's say that we want to take the limit as x goes to a of f of x minus lm of x, which is what we found here, this one over here, over x minus a cubed. Now we want this to go to 0. And we're going to see again, if I plot x minus a cubed, we're going to see that all of a sudden our approximation, isn't that good anymore. They're basically the same. If we zoom in, they're basically the same approximation. It's not like our approximation is infinitely better, which again means we're going to have to, so this limit, if we take the limit, the initial one here, but if we just change the square to cubed, this won't go to 0 anymore. So we have to add yet another term. So our lm of x is going to be exactly what it was before. So it's going to be, it's going to be f of a plus f prime of a, blah, 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 till the end. And we're going to add another term, plus m x minus a cubed. And again, if we take the first derivative and the second derivative, these all just cancel out. So we're still going to get that lm prime of a equals f prime of a, because when x is a, this just cancels. And again, we're also going to get that the second derivative equals f times the second derivative of a. So it doesn't affect lower order terms, because again, when x is close to a, x cubed will be a very small number. And if we want to make this limit go to 0 again, we're going to see, we're going to do the exact same thing. I'm not going to do now. If you want, you can do it at home. But we're going to have the limit as x goes to a of f of x minus lm of x, which is this new thing, over x minus a cubed. And again, if you expand this and you plug in x minus a, you're going to see we get an indeterminate form 0 over 0. So you can use the L'Hopital's rule. And then you're gonna see that it goes to 0 again. So you can use the L'Hopital's rule again, and then you're basically gonna get to a point where you can again just find. You're gonna see the definition for the third derivative of f, and basically what you're gonna find, if you do this at home, is when you evaluate this limit, you're gonna get 1/6 f of a minus m. So you're gonna see that this goes to 0 only if m equals 1/6 f of f, the third derivative of f at the point a. This is the only m which is going to make this quotient go to 0. And again, if we check over here, this is if we add our x minus a cubed, and we add our our cubic approximation over here, bang, we're going to see again it is way better. If we delete our old approximation, our old approximation was about the same as the x minus a cubed one. This new approximation is way better than x minus a cubed. And again, it is small o of a minus x of x minus a cubed. It is infinitely, it goes to 0 way faster than this function. See, it is a way better approximation. And then we can keep on playing this game with the error function, and we want to make it way better than its respective x minus a squared, x minus a cubed term. And basically, what we're going to see, what we're going to find in the pattern, then we keep on adding a term. Then we're going to add m x minus a to the 4. And again, we're going to make this quotient go to 0. And what we're seeing here with the pattern, 1 over 6, well, that's just 1 over 3 factorial. And 1/2, that's just the same as 1 over 2 factorial. So basically, we just built the Taylor series. Our approximations, are going to be exactly f of x minus, it's going to be, it's going to be f of x plus f prime of a x minus, this is going to be f of a plus f prime of a x minus a plus, 1 over 2 factorial f double prime of a x minus a squared plus 1 over 3 factorial f triple prime of a x minus a cubed, and that is exactly this sum over here. If you keep on providing these limits and minimize the error, we're gonna be getting such m's such that we get again the derivative, f cubed of a over 3 factorial x minus a to the power of 3. And again, as we sum this to infinity, because we're minimizing the error, we always, the error will always go to 0 infinitely faster than these terms respectively. At infinity, this function has to equal exactly this function, because it is, the one that minimizes the error as fast as possible. It is the best possible approximation. And if we have an infinite amount of these approximations, they have to equal this function exactly. So that is how you get the Taylor series through error minimization. I hope it makes a bit more sense now. I felt like the video was slightly confusing, but I hope at least it kind of makes sense. And again, it's very nice examples for here with decimals, where you can actually plot it and see that your error goes to 0, way faster than these respective terms. It's pretty clean to see, and then we can just get these better and better and better and better approximations. I think it's very clean to actually look at them, compared to our function e. For example, e to the x. E to the x was just one function. We can do this for any function we want. So yeah, that is it. Thank you for watching.